Right, we're about to start day 22. So let's take a look at that. I was trying to think if there's something else I wanted to do before getting going, but I don't think so. Um, so let's just push right in. Day 22, grid computing. You gain access to a massive storage cluster arranged in a grid. Each storage node is only connected to the 4 nodes directly adjacent to it. 3 if the node is on the edge, and 2 if it's in a corner. All right. So we're going to be doing some grid traversal. You can directly access data only on node/dev/grid/node-x0y0. Okay. But you can perform some limited actions on the other nodes. You can get the disk usage of all the nodes via df. That's a Unix command, yeah, as it says in the link down there. The result of doing this is your puzzle input. Oh, okay, yeah, let's get the puzzle input. Get input 2016, 22. There's 902 lines. Okay, I see. It looks like it's a 35 by 24 or 36 by 25 since it starts at 0, 0. All right. You can instruct a node to move, not copy, all of its data to an adjacent node if the destination node has enough space to receive the data. The sending node is left empty after this operation. Nodes are named by their position. Node x10, y10 is adjacent to x9, y10, 11, y10, 10, y9, and 10, y11. Okay. That makes sense. It's just a grid. Before you begin, you need to understand the arrangement of data on these nodes. Even though you can only move data between directly connected nodes, you're going to need to rearrange a lot of the data to get access to the data you need. What's the data I need? Oh, the question is how many viable pairs? Okay. To do this, you'd like to count the number of viable pairs of nodes. A viable pair is any two nodes A, B, regardless of whether they are directly connected, such that node A is not empty, its used is not 0. So that's this middle column here. Nodes A and B are not the same node. Okay, that's just a, yep. And the data on node A, it's used, would fit on node B, its avail. So the 67 won't fit in any of these, right? Because these are the avails. These are all 60 and above, and all the avails are 30 and below. What am I missing? Oh, this one. Oh, no. This one's got 499 and only 2 avail. Yeah, all of these are 60 and above, and all of these are... So how is that going to work? I'm just scanning through the data here, and it doesn't make any sense to me. What am I missing? All right, well, we'll figure it out, I guess. We can at least count how many viable pairs there are. There might be 0. That would be annoying. All right, we got the puzzle input. Let's go here and set up the code here. Mod. Let's do this. Let's do this. And then down here, 22. Oh, did I move off the screen? I did. Okay, there we go. All right, so this should fail to build, but then we can do the code action to create the file, and then jump to the file, and then go create this, 2016, 22, and then we should get an unsolved. Perfect. All right, so I guess the first thing we do is parse the input and then save the node, the used and avail. It looks like we don't need size. Size is just going to be used plus avail, right? Let's take a look at that input again. Uh, 67 plus 27 is 94. That's correct. Okay, so maybe let's just scan another one here. 11 and 498 is 509. That's correct. 17 and 73 is 90. Yes, it is. Okay. So size, I guess we could ignore that because we'd be able to figure it out from used and avail. Or maybe we need that when we're moving nodes around. All right, well, we'll save it. Let's create a struct called node. It's a grid node. And it has XY coordinates. Or should we make it a location? And that could be XY. I don't know. Let's find out. Right now, we don't even care about the location, right? This is going to be ignored. So let's do that. All we care about is the used and avail. So let's have a used and avail. And then we can just parse out that data. For the parser, what do we need? Oh, right. Before we do anything else, let's git add input git commit -m 2016 day 22 input. No, oh, right here. No verify. Is that what it is? Yes. Okay. All right. Let's try again now. So we know what the input looks like, sort of. It has to go in here. We need a grid node. Backup grid node. And then this becomes node vec new. And then we can just, in the parser, we just fill it in. Oh, let's take a look at the input again, right? Okay, so this is what the input looks like. Looks like we have to ignore the first two lines. So we can say let lines equals AOC lib, read lines, input 2016-22.text. And then we can say for L in lines iter skip 2. And then we just need to split it by white space. And then we can parse out the used and avail. Looks like the used percent we can ignore and the size we can ignore, right? So all we have is the location and the used and avail, because that's all we need. And then maybe part 2 will need more data. But we'll figure that out when we get to part 2. So the first thing we do is let call is equal to l.split white space dot collect vec stir, like that, and that should be just a bunch of stirs. Yep. And then this we can get the xy by doing a split on a minus. And these values here, we have to strip off the t. What's the easiest way to do that? Let me put this in a comment so I'd be able to actually use some of the features here. Yeah. All right. So we can say let location is equal to call of 0 dot split on the dash. Can I do skip 1? Collect vector. Can I do that? Oh, it does. It lets me do that. Okay, and then we need to pop off the first character and parse the first thing as the, okay. So then we can say let lock equals, and we're going to make a tuple, because that's what we put in here, is a tuple. And so we just parse it as usize, lock of 0, no, 1 dot dot, lock of 0, 1 dot dot. Can I do that? Parse usize unwrap. And then 1. Will it let me do that? It does. Nice. Will that fit on one line? It won't. Not nice. Okay, so that's the location. And then we need to parse out a U size for each one of those. And that's column of 2 and 3. We're ignoring column 1 here for now. So column 2 would be used. Let used equals call 2 of 0 dot dot call 2 dot len minus 1 dot parse U size unwrap. All right, and then avail. Change the 2's to 3's. That's a little weird doing it this way. I have to strip the T off, otherwise the parse will fail, right? And then we say self, I've forgotten what I called it. Self node. Should I call it nodes, plural? That's a big controversy, whether the arrays should be named plurally or singularly. Nodes push grid node lock used eval println and then self nodes len. And how many lines was it? Where did I do the get? I've lost it here. Here it is, 902 minus the first 2 lines, so it's 900. Okay, so there should be 900 coming out of this. And it doesn't like that. Oh, underscore, right. Yeah, 900 right there. Perfect. All right, so we're on our way, and now we just need to check for what viable nodes. Node A is not empty. Node A and B are not the same node. And the data on node A would fit on node B. Okay, so if there's 900 nodes and half of them can fit in the other half, what kind of number are we looking for here? This is n squared. What's 900 squared divided by 2? So we're looking for like on the order of 400,000? Something like that? So down here we can say for, I guess we can use A and B since self nodes len for B in 0 dot self nodes len. I mean, yeah, it's only checking a million things, so it should go pretty fast. I don't know if there's probably a faster way to do it. Okay, so node A is not empty. If self nodes A dot used is equal to 0, then continue. We could do a single if statement, right? If node self nodes A dot use is not equal to 0, and A is not equal to B, and self nodes used A used is less than or equal to self nodes B dot avail, right? Then we increment the count. Which I haven't defined yet. So let's do that. Let mut count equals 0. This probably be better with a function composition thing. This, oh, only 864. Did I do something wrong? That doesn't seem, well, let's try it. Ah, okay. That is the right. There's only 864 nodes are viable nodes. That's interesting. What does Clippy say? Clippy is fine. Can I do this differently? I should be able to say self nodes iter filter B self nodes A. Oh, I can, yeah, this is where I can do the if here. I can say if self nodes A used equals 0, continue. Now it makes sense to do it, because if I do this, and I can say A is not equal to B, and self nodes A dot used is less than or equal to self nodes B dot avail dot count, and I can say count plus equals. Will that still give us 864? No, it won't even compile. Oh, because B is a grid node. Not a, oh, yeah. So maybe we can compare locations. Self nodes A dot lock not equal to B dot lock. And it's just B dot avail. Okay, and if I hit run, is it still 864? It is. Okay. Is that is that better or worse? And we should also be able to do it up here, although I don't know if you can iterate self nodes inside the self nodes. I don't think you can. Although it's not, we're getting non-mutable things, so maybe we can. Let's try it. Self nodes iter filter A dot used is not equal to 0 dot something dot this fold 0 AB oh, we don't want, yeah, we want count and A, and then we can say this can I get rid of that, and then that's the end of the fold, right? And then say let mut count equals that. It formats. It does not compile. Oh, I can't use the, let's call it sum, and then sum plus. Nope. Oh, it doesn't have to be. Oh no, it came up with 864. And all we have to do is remove the count, mute on the count. Okay. So that's fewer lines of code, but a lot harder to read. Now we're using the location, so I can get rid of the underscore on these guys. Yeah. I don't know if that's faster or slower, but it's more rusty, maybe. I'm surprised that this doesn't format into new lines, but it all fits, so we're all good. Yeah, I like it. I'll take it. And Clippy likes it. Good. Git status. Git add source. Git commit -m 2016 day 22 part 1. All right. What is part 2? Now that you have a better understanding of the grid, it's time to get to work. Oh, okay. Your goal is to gain access to the data which begins in the node with y = 0 and the highest x. That is the node in the top right corner. Okay, for example, suppose you have the following grid. In this example, you have a storage grid, 3 nodes wide, 3 nodes tall. You can access 0, 0 directly. So this guy up here. It's almost full. Node containing data you want to access is over here. Right? Contains 6 terabytes of data, enough to fit in your node. Yeah, so they don't care about the size. They only care about used and avail. Oh no, this is used in size. But the size here, right, the used here can fit in here if we can move the data out of this one. Okay, understood. Node x1, y1 looks like it has enough read space to enable you to move some of this data around. In fact, it seems like all the nodes have enough space to hold any node's data except for this guy, which is much larger, very full, and not moving anytime soon. This one. Okay. So initially the grid's capacities and connections look like this. Node you can access directly is in parentheses, right here. The data you want starts in the node marked by square brackets. Okay, so to simplify it here, we have something that's too big to do anything with, an empty node, the goal node, and the destination node. The goal is to move the data in the top right to the node in parentheses. To do this, we can issue some commands. Now, we did see something similar to that, didn't we? If we look here, all these used cannot fit in any of these avails. So do we have any node that this 67 can fit in? Sort plus 1, 2, 3. Input 16, 22 less. All right, so these are all very small and have a lot of data. So maybe these guys are the equivalent of this example here, where it's too much to move. They're too big to fit anywhere. Let's see, what's our biggest one? Oh, 85. And it's empty. And it's at 1722. Okay. But the next biggest one is 30. Huh. Okay, wait a minute. Let's sort by used. So we have an empty node, and then the next smallest capacity is 64. So what we have is a situation where we have one node that can receive data and no other nodes that can receive data, because the smallest amount of data to move is larger than the next largest. So it makes a search space really small. Well, smaller than the million nodes that we were looking at earlier. Because there's only one. So this is like a 15 puzzle, but in a big grid, I guess. Because you have one empty space that you can move around. And then we need to get the goal data. And so wherever that is, 1722, let's see if we can reason this out. We can move the empty spot all the way from 1722 all the way up to near the goal. And we want to get the goal over to the left, right? So we want to move the empty spot to the left of the goal data, and then move the goal data over, which moves the empty spot here. And now we want to move the goal data there, so we have to move the empty spot down 1, left 2, and up 1, and then we can get the data. So wait a minute, let's see if that's what they talk about here. Yeah, so we start here, we move it there, we swap these positions. This comes down, left, left, up. Okay, that makes sense. And then we move the goal. Okay, so all we need to do is figure out how to do that. Can we print out? What we can do is we can display the grid like this. Let's see what we've got right now. Let me get rid of that. So here we print that. We don't need to print that out anymore. But what we can do is look at how do we print this out. I want to just take a visual look at what our data looks like. So any data that's greater than any data used that's less than the size of the empty node can be moved. And that's where we got the 864 actually. So we have 864 nodes that can be moved, which means there's 36 nodes that can't. And that must be all those ones that have a giant number in them. What we can do here is actually, while we're parsing, we can save off largest. We could save the largest one in terms of avail, right? Largest equals largest max avail, right? And then that should be that 84 or 85 or whatever it was. Let's see. Oh, that failed. Oh, because I forgot to make it mutable. There it is. It's 85. Okay. So we can then run through the grid. Oh. I was just thinking, okay, how do we do this? But yeah, we have this as an array of xy's, and it's increasing x's. Oh no, it's increasing y's. That's not good, because I want to print this out as a grid. Well, I guess I could print it out as a rotated grid, right? Yeah. But that'll be harder to do. Let's let's save max x and max y. And then we can just loop over them. Max x is equal to max x dot max of lock dot 0, and max y is max y of lock dot 1. And then we should be able to say for x in 0 dot dot equals max x. Oh no, we want to do rows first. Rows first, and then for x in 0 dot dot equals max x. Oh. Then I want to look it up. Do I want to change this to a hash set that's indexed by, instead of having a vector, we'll just make it a hash map? Let's do that. Use standard collections hash map. That's going to mean changing part 1. Okay. Hash map of use size, and a grid node. And a grid node doesn't take that anymore. And then here we say insert lock this guy. Oops. And now this completely changes. And the only reason I'm making this change is so I can print the grid out. But let's see, we can iterate over all the nodes. We can still do this. It's this part here that's throwing me off. So how do we get, if I do that, oh, it's saying unknown. Because self nodes should be able to filter. Why is it saying unknown? Oh, because I messed this up. Let's try again. Yeah, now it says grid node. So a dot, and that's interesting. It's passing it in as a, so we can say a lock, a node, and that's still usize, and that's the pair. So we don't actually need that, right? And now A is this, is the location plus the grid node. So we can say A dot 0, and then B is going to be, yeah, B dot 0, and A dot 1 dot use is B less than B dot 1 dot avail, right? Yeah. Okay, so that should still give us that. And this should build. And it doesn't. What am I doing wrong? Oh. No, okay, and we're still coming up with A64. Okay. So we successfully made that change. So now we're going to say if self nodes get xy dot unwrap dot used is less than largest, then we'll print bang a dot, right? Because we're doing dots for spaces that fit and then hash for spaces that don't. So we can do dot else print hash, and then after this println. Okay, so let's see what that looks like. Interesting. So this is all like all here. Okay, one other thing I'd like to do, let used is equal to this. If used is equal to 0, then we'll print out the underscore. Right? Else if used is less than largest. So where's that underscore show up? Right here. Interesting. And the goal is up. Oh, okay, we can actually print the G, right? If x is equal to max x and y is equal to 0, print bang G. Else. And that should put a G. It does. Look at that. The G goes right there. Okay. This is interesting. So this basically becomes move this thing all the way over here, move it all the way up to the top, move it all the way to here. So however many moves that is. And then plus that sequence of events that gets us from here to the beginning. And how many moves is that? So we're here. We're assuming we're at this position here. So we need 1, 2, 3, 4, 5 to get back. to that, and then plus 1 final 1 at the end. So we need a sequence of 5 steps to go from this state here to this state here, which just basically shifts these two over 1 to the left. And so that'll shift us 1 to the left 5. So it takes 5 moves. Right? That's how we care. What's the fewest number of steps required to move your goal? I never actually read this, but I kind of assumed. I shouldn't have done that because sometimes it can get tricky with that. What's the fewest number of steps required to move your goal data to known x0, y0? All right, so this has to move all the way to the beginning. So it's equal to x. I guess I should save these in self then and save largest, or we don't care. We should save the location of this guy. So we need to put that here. So empty is going to be a usize. That's going to be this guy here. And then width and height. And then down here, instead of doing this, we just say self width is equal to self width max x, self height is equal to self height max y. This can go away. And then we should be able to print this out in part 2. So let's try that. Self height, self width, self width. Oh, right, we don't have we need to save largest. And I have to do self largest. Can I? Oh, for new, I still need a new. Can I call default? Will that work if I derive default? Because I don't care what the values are. Yeah, okay. Very good. So if we look at this, here's the underscore. We just need to move it to the left. That takes that many number of moves, whatever distance that is. We need to move it to the top. So it's just the XY location of that plus that width, which is the width of the thing minus 1. So that's how many moves it would take. Total moves is equal to this guy. So let's save this guy. Let mut empty is equal to none. Empty is equal to sum xy. And then we can say if let empty sum empty is equal to empty, which it should. Because if it doesn't, then we have a problem. Else 0. Okay, so it's going to be empty dot x plus empty dot y plus self width minus 1. Right? And that'll get us to this location here. And then we can just print that out. And, oh, right. That's a tuple, not an XY thing. Okay. So, oh, and unfortunately, Bacon likes to cut things off. Oh, yeah, so we don't actually need to save empty here because we're not using it. All right, there we go. Now it says 73. So it's 73 moves to get from here to here, from here to here, and from here to here. And now we need 5 times to get to this thing to get, yeah. So for each one of these, it's 5 times that, because you have to go 1. I'm going to move my cursor to where the empty should go. 1, 2, 3, 4, 5, 6. So for here, 1, 2, 3, 4. No, that's right, 5. Right, because now the G is here. 1, 2, 3, 4, 5. So this takes 5 plus 5 plus 5 plus 5. So it's 5 times the width of this minus 1. Five times self width minus 1. Let's just put that here, because I can just change that to 6 times self width minus 1. And then that'll end us up with the underscore there and the G there. And then we only need one more move to move the goal into the spot where it needs to go. So I'm guessing it's 244 moves. Let's see if I'm right, or if I'm off by 1. There you go. That's the right answer. Okay. So we can change that to 6 times and get rid of this extra multiplication. And then we can not print this out. All we need to do is find the empty. Oh, right. Duh. That's what I had from before. We can find the empty one here. Empty. Lock. And if we don't need to print everything out, then it's okay to just do it this way. Right? We can blow this all away and change this to self-empty, self-empty, and then come up here, and then we can just look for used as 0. If used is equal to 0, self-empty is equal to lock. And then this should still have usize, usize. And oh, we don't need to do this anymore. We can just say this. So that's still 244. It is. And now we can just print it directly. Create output. 244. That's interesting. This took 81 milliseconds to run this double. I wonder if there's something we could do that's faster here. I don't know. Parsing took 15. But we were doing some work in here in order to, like, this thing is a bit of work. And these 2 lines is actual work to help solve the problem. All right. I mean, I can live with this as the answer, or as my final solution. Clippy's okay with it. So I can't really complain. I wonder if we can do this automatically. I'm going to try that for the next one, whatever the next one is. Okay, git status. Git commit -am 2016 day 22 part 2. All right. Should we keep going? We're so close.